Hello dear student, welcome to today's class. Today's topic is dipole and the dipole moment. Let's start with the definition of dipole and dipole moment. Here at the picture we have seen there are two charges, one is positive q, another one is negative q. From the positive q to negative q, the distance, let's consider this is r equals to 2a. So from the midpoint up to the positive charge is a, and from the midpoint up to the negative charge is a, so r is equals to 2a. It means there are equal charges and they are opposite each other, and obviously this 2a or r equals to 2a, r is equals to 2a is very small. If complying these three conditions, it means the system is dipole. So the definition of dipole will be a system having two equal and opposite charges are separated by a small distance. So dipole done. Let's start with the dipole moment. As I said, the distance between these two charges is very small, and that distance is 2a, and the charge, either charge is q. So the definition of dipole moment, let's start with the mathematical equation or mathematical expression. So either charge q times the distance 2a, it means that the dipole moment is the product of magnitude of either charge and the dipole length 2a is called the dipole moment. So the unit will be coulomb and obviously meter. This is the unit, right? So the two equal and opposite charges separated by a small distance combination of charges is actually an electric dipole, and the strength of electric dipole measured the dipole moment. For dielectric at the axial, it means that if there is a two charge minus q and positive q, they are separated obviously a distance of 2a, and if you'd like to determine the electric field and the potential at the axial of the dipole, it means this is the line obviously and this is the axial as well. So at this point, consider the p. At this point, the electric field, the mathematical equation will be 1 by 4 pi epsilon naught, and obviously from the midpoint of the dipole, it means two charges, this is O, and from O to P this distance is considered r. In that case, 2 of the dipole over the r cube. This is the empirical equation of electric field when dipole at the axial, and obviously the potential V is equals to 1 by 4 pi epsilon naught E cos theta over r square. From the electric field equation, we can observe that the electric field is directly proportional to the dipole moment, and of course the electric field is inversely proportional to the cube of the distance from the observation point of the midpoint of the dipole, as the dipole moment at axial positioned. As a result, the theta will be 0 degree. In that case, the potential simplified equation will be 1 by 4 pi epsilon naught, and cos 0 degree is 1. It means P over r square. So the mathematical expression of potential V is directly proportional to the dipole moment, and obviously the potential is inversely proportional to the square of distance r of the observation point of the center of the dipole moment. The second case, equatorial point of an electric dipole. It means in between the dipole or the midpoint of the observation of the dipole, let's say this is O, and P is this point, and obviously minus and positive charges. For these two charges, the electric field occurred. Obviously for positive charge, electric field E2, and for negative charges, electric field within this direction, and the net electric field will be within this direction, and the total electric field for equatorial point of dipole will be 1 by 4 pi epsilon naught dipole moment over r cube. From the equation, we can observe the dipole is directly proportional to the dipole moment, and electric field decreases over the distance, and the potential will be 0 for equatorial. Here I am not explain how this equation or empirical equation comes from, the derivation of the equation not I am presenting within this lecture. I will do this another lecture. Anyways, here a very important point, that is, first of all, the dipole moment direction towards positive. This is both case, obviously for equatorial and obviously the axial as well. So what I'm saying, the dipole moment towards the positive charge, it means that, so from the observation point, the dipole moment will be within this direction. So this will be the dipole moment. And second point said, the direction of electric field is always opposite to the dipole moment. So electric field is in this direction and dipole is this direction. And for this picture and this picture, what are the differences here? Here negative charge taken at the left side and the positive charge is taken at the right side. Here positive is here and negative one is here. In that case, obviously the dipole moment will be towards the positive direction mentioned, and obviously opposite, the electric field will be in this direction and potential will be 0. Now torque. Characteristics of torque acting on an electric dipole. If within a dipole a torque is experienced, it means the rotating motion experienced in the time, the torque actually a measurement of a force that can be object to rotate about an axis. So obviously this is the dipole positive charge and the negative charge. So this is the dipole, and due to this dipole, a force vector will be this one, which is designated as the force F. By the definition of torque, we could write down the force and the distance between the force, that is actually d. And obviously by the definition of force, we could write down charge and the electric field, and the distance we could write down 2 of a. So let's write down 2 of a sine theta, because within the dipole, say this is the lever arm vector, and obviously this is the force. So in between, this angle is called theta. So here we know that the dipole P equals to Q over 2A. So we could write down P time electric field and sine theta. So this is the equation of torque, the basic equation. Now for case 1, so let's consider, let's use another pen. So this is case number 1, okay. Here we could say the dielectric pole or electric dipole is parallel. It means the theta is equals to 0 degree. Or we could say for case number 1, the dielectric pole gets aligned with electric field. It means theta is equals to 0. In that case, torque is equals to Pe sine 0 degree. So we'll get the value is 0. This is the minimum value. Again, for case 2, so this is case number 2. Case number 2, when electric pole is antiparallel to the electric field. So dielectric pole within this direction, let's use this color. So this is the dipole and electric field is this direction. So they are parallel, but they actually anti-parallel to the electric field of the dipole. So here obviously theta is equals to 180 degree. So tau is equals to Pe sine 180 degree. So here also the value of torque is 0. Again, case number 3. So case number 3, actually the dipole. So where is dipole? Obviously within this direction. We know dipole always towards the positive charge, and electric field is in this direction. It means the theta is equals to 90 degree. It means the torque, the value of tau is equals to Pe sine 90 degree. So we could find the value of Pe. So when the electric field is parallel to the electric dipole moment, then we'll find the maximum torque. Here the small amount of angle d theta against torque working on it. Obviously when it's rotating, it means there a torque experienced which is against the dipole, and due to this rotation a small amount of work have done. So amount of work done is equals to the torque and the small amount of angle. And obviously the small amount of work done because of or due to the external agent. So these lines actually represent the external agent. Obviously these lines are external agent. Here the external agent is nothing but an external electric field placed within this region. So this work done actually experienced due to this external electric field. The value of tau or torque is equals to dipole moment and the electric field and sine theta d theta. Now if you'd like to find the value work done W, what we have to do? We have to integrate both sides of this equation. As here integration for rotation, say the very initial angle, say this is theta 1 and this is theta 2. So the lower limit is theta 1 and the upper limit will be theta 2. Now find out the integrated value. So PE here theta 1 theta 2 sine theta PE. So the integration of sine theta is equals to minus cos theta. Let's put the value here theta 1, the lower limit, and obviously the upper limit is theta 2. Now if we say initially the dipole oriented is perpendicular to the direction of electric field, it means theta 1 is equals to 90 degree, though this figure is not absolute for this condition actually. So what I'm saying, the very first orientation perpendicular to the direction of electric field, theta 1 equals to 90 degree, and then brought to some orientation theta, angle of theta, it means theta 2 is equals to theta. So the work done will be, so this minus here PE and cos theta, let plug in the value here, lower limit will be 90 degree and the upper limit will be theta. Therefore the final work done will be PE cos theta. So now case number 1. For case number 1 represents the potential energy of dipole is minimum when dipole moment is parallel to the external field. By the way, I forgot to tell that as this is positive and this is negative, obviously there will be a electric field within these two charges, right? But this electric field E is an external electric field, this is an external electric field, and this is an external electric field. So I'm talking about this external field. Anyways, what I'm talking, when the dipole moment, so this is the dipole moment, is parallel to the external field. So this is the dipole moment and the electric field, external electric field is this one. So they are parallel. It means that the theta is equals to 0 degree. In that case, the total energy is minus P of E. Now, the case number 2, position of unstable equilibrium. Here, the potential energy of dipole will be maximum. It means here theta is equals to 180 degree and the energy will be positive dipole times the electric field. It means the potential energy of a dipole is maximum when the dipole moment is anti-parallel. It means this is the external electric field and obviously dipole moment within this direction, I mean towards the positive direction. It means within this straight line is 180 degree. So when it is 180 degree, then we'll get the maximum energy of PE. Case number 3. So case number 3 is position of zero energy. In that case, the theta will be 90 degree and the potential energy will be 0. It means when the external energy is perpendicular to the dipole moment, in that case we will find the zero energy. So let's summarize here. First of all, dipole and dipole moment. So for dipole and dipole moment, obviously two equal and opposite charges and very short distance 2a. So the system is dipole and dipole moment is nothing but P equals to the either charge and the total distance. So unit will be coulomb meter. For axial point and electric dipole, so here is a negative charge and here is a positive charge. So in between these two charges, dipole system will be experienced, and obviously towards positive charge, dipole moment is this one, and we know the dipole moment is always opposite to the electric field, or vice versa. The electric field is opposite to the dipole moment for both cases actually. For axial case, this one, and there is another case is equatorial point. So there is a charge minus q, and this is a positive charge. So this is the observation center point O or P, whatever. So the distance between these two charges obviously 2a. So the dipole moment obviously towards the positive. So this is the dipole moment direction. And as I said, for both cases, obviously equatorial case, the electric field will be opposite to the dipole moment, as I said. So both cases, dipole moment is this direction. It means electric field will be opposite direction for both cases. And obviously in both cases, electric field is proportional to dipole moment and inversely proportional to the cube of the distance r, very simple as. And for axial case, potential will have a value, and for equatorial, potential will be 0. And for torque, we know P of E. So the unit will be here coulomb meter, and electric field is nothing but Newton per coulomb. So coulomb cancel out. So the unit of torque will be Newton meter. And obviously dipole moment is a vector quantity. And of course the direction of dipole moment always from negative charge to, this should be negative charge to positive charge. And electric field for axial is equals to 2 times of equatorial axis.